Lecture 2 is all about the natural logarithm, and this function is defined as the antiderivative for 1 over x. We look at the properties of the graph of this function, and then we derive the algebraic properties of the function, which you may have seen before. We consider limits involving the function. We extend the domain of our antiderivative using the absolute value of x, and this allows us to derive some formulas involving derivatives and integrals with the natural logarithm. Lastly, we look at the method of logarithmic differentiation. So let's have a look at the definition of this new function, the natural logarithm. From Calculus 1, we have a formula for the antiderivative of x to the n. Namely, its antiderivative is x to the n plus 1 over n plus 1, except in the case when n is minus 1. In other words, x to the n is 1 over x. The fundamental theorem of calculus allows us to create an antiderivative for this function x inverse because the function 1 over t is continuous on the interval for t between 0 and infinity. We have this function of x, the definite integral from 1 to x of 1 over t, where x is greater than 0, is an antiderivative for the function 1 over x according to the fundamental theorem of calculus. In other words, the derivative of this function is 1 over x. We give this new function a name. We call it the natural logarithm of x. Let's have a look at what the graph looks like using Mathematica. We can create a picture of the natural logarithm using Mathematica. By definition, the natural log of x is the area under the curve y equals 1 over t, shown here in blue, between 1 and x when x is bigger than 1. So for x bigger than 1, for example, x equals 7.62, the natural log of 7.62 is the area under this curve, y equals 1 over t, between 1 and 7.62. Here we plot the natural logarithm right below. So for x equals 7.62, the natural log of x is this area in blue above. We see that as x increases, obviously this area increases, and the natural logarithm is always increasing. Another way to show that is, by definition, the derivative of this function is 1 over x, which is positive, so therefore the function is always increasing. In fact, we can use both the first and the second derivative to show that the function is always continuous, it's always increasing, and it's always concave down. If x is less than 1, what does this definition mean? Well, when x is actually equal to 1, this area must be 0, because it's the integral from 1 to 1 of a function 1 over t, but since the endpoints of the limits of integration, of the interval of integration, are equal, the area under the curve from 1 to 1 is 0, so the natural log of 1 is 0. When I move to the left of 1, if I take an x value below 1, what happens? I get the integral from 1 to 0.5, say in this case, for x equals 0.5, of 1 over t dt is a negative number. The reason for that is that the area, this blue area here, is in fact the definite integral from 0.5 to 1 of 1 over t dt. And the natural log of 0.5 is the integral from 1 to 0.5 of 1 over t dt, which is minus the integral from 0.5 to 1 of 1 over t dt. In other words, it's minus the area. So, to summarize, we have a function, the natural log of x, which is negative for x less than 1. Its domain is every x value between 0 and infinity. It's increasing, continuous, concave downwards, and in fact we'll show in class that as x tends to infinity, the limit of this function is infinity, and as x tends to 0, this function tends to negative infinity. This function is always increasing, so we can derive that it is 1 to 1. And in fact, you can see that when x is bigger than 7, this function ln of x is bigger than 1. And when x is equal to 1, this function ln of 1 is equal to 0. So therefore, by the intermediate value theorem, there must be some point where ln of x equals 1. And because the function is 1 to 1, this point is unique. So there's a unique number for which ln of x equals 1. In other words, the area under the curve from 1 to x is 1, and that's a very special number which we call e. I've marked here e here in green, and it's approximately 2.66. We will also prove the following algebraic properties of natural logarithms by comparing derivatives in class. So we already know that the natural log of 1 equals 0, and we can also derive that the natural log of a times b is the natural log of a plus the natural log of b, and the natural log of a to the r is r times the natural log of a. And these properties will be used to simplify expressions in order to use logarithmic differentiation. For example, the natural log of x plus 1 squared times x minus 1 cubed all over x plus 2 to the power of 4 can be expanded as follows. It's equal to the natural log of the numerator minus the natural log of the denominator and then we can further break up this first expression as the natural log of x plus 1 squared plus the natural log of x minus 1 cubed minus the natural log of the denominator. And now we can use the power rule to simplify that further. That's twice the natural log of x plus 1 plus 3 times the natural log of x minus 1 minus 4 times the natural log of x plus 2. We will also verify the following limits in class. We have the limit as x goes to infinity of ln of x is infinity, and the limit as x goes to 0 from the right, because the natural log is only defined for x greater than 0, of the natural log of x is minus infinity. And we can use these limits to calculate other limits. For example, suppose I want to calculate the limit as x goes to infinity of ln of 1 over x cubed. Well, I have to find out what's happening this 1 over x cubed as x goes to infinity. So I'm going to let y equal 1 over x cubed and examine its behavior as x approaches infinity. As x goes to infinity, 1 over x cubed will go to 0 because the x cubed gets larger and larger, and it's always positive, so it'll go to 0 from the right. So now I can rewrite this limit as the limit as x goes to infinity of ln of 1 over x cubed is equal to the limit as y goes to 0 from the right of ln of y. Now that's exactly the same as the limit up here. It's just got a y instead of an x, so that's negative infinity. We can expand the domain of our antiderivative for 1 over x by using absolute values. And we have the natural log of the absolute value of x is the natural log of x if x is bigger than 0, and the natural log of negative x if x is less than 0. Here we have its graph, and obviously it's not defined when x equals 0. And in fact, if we differentiate this function, we see that its derivative is also 1 over x, but it's defined, it has a larger domain than the natural log of x. So this gives us two formulas. The derivative with respect to x of the natural log of the absolute value of x is 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x plus a constant. We can combine this differentiation formula with the chain rule to get that the derivative with respect to x of the natural log of the absolute value of some function g is the derivative of this with respect to g of x times the derivative of g of x with respect to x. In other words, that's g prime of x over g of x. Let's look at an example. For example, suppose I want to calculate the derivative with respect to x of the natural log of the absolute value of cosine of x. Well, this is my g of x, and in fact I'm going to let u equal cosine of x. And I'm looking for the derivative with respect to x of the natural log of the absolute value of u. And according to the chain rule, this is equal to the derivative with respect to u of the natural log of the absolute value of u times the derivative of u with respect to x. And now this follows directly from the formula. This is equal to 1 over u. And the derivative of u with respect to x is the derivative of cosine of x with respect to x. And that's equal to minus sine. So this is 1 over u, which is 1 over cosine of x, times minus sine of x. And that's equal to minus sine over cosine, so that's minus tangent of x. We can reverse these formulas to get some formulas for integration. And in fact, we just need the formula on the left here because we can use substitution to derive the answers given in the formula on the right. So, for example, suppose that I want to integrate, suppose I want the integral of 2x plus 1 over x squared plus x dx. I let u equal x squared plus x, and using substitution I get du is equal to 2x plus 1 dx. This gives me that this integral is equal to the integral of du over u, or 1 over u du, and then by our formula, that's the natural log of the absolute value of u plus a constant. And now, substituting for u again, we get that that's the natural log of the absolute value of x squared plus x plus some constant. The last topic on our list is logarithmic differentiation. And to apply this, if we have a very complicated function f of x, say for example f of x equals x plus 1 squared times the cubed root of x plus 2 all over x minus 10 squared. So we can break this function up using logarithms. And so we write this equation y equals x plus 1 squared times the cubed root of x plus 2 all over x minus 10 squared. And if we're looking for the derivative of f with respect to x, we're looking for dy dx here. Now we introduce an extra step which ultimately makes the problem easier. We take the natural log of both sides. So we take the natural log of both sides of this equation, and we have the natural log of y on the left equals the natural logarithm of this complicated looking thing, which gets much easier when we apply the natural logarithm. So we can expand that and simplify it in the process. On the right-hand side, we have the natural log of x plus 1 squared plus the natural log of the cubed root of x plus 2, which is x plus 2 to the 1 over 3, minus the natural log of the denominator, x minus 10 squared. And we can simplify further. We can take those exponents and put them before the natural logarithm. And now the point about this is it's very easy to differentiate the right-hand side. But of course when we differentiate the left-hand side, we don't quite get dy dx. We have to use the chain rule, and instead we get 1 over y times dy dx. So the derivative of the left with respect to x is the derivative of the right-hand side with respect to x. And on the left here we use the chain rule. So the derivative of the natural log of y with respect to y times the derivative of y with respect to x is what we get on the left, which is 1 over y times what we're looking for, dy dx. And on the right-hand side, we get the derivative of 2 times the natural log of x plus 1 with respect to x, which is 2 over x plus 1, using the chain rule and multiplication. Here we get 1 over 3 times the derivative of ln of x plus 2, which is 1 over x plus 2, times the derivative of x plus 2, which is 1, minus 2 over x minus 10. And now we're looking for this dy dx, so we multiply everything across by y. We get dy dx equals y, but y is equal to all of this here. So I can get an expression for y in terms of x. So it's y times what I have there on the right-hand side. And then that's equal to this complicated expression in x times all of this. We'll do more examples in class.